So today we'll start the first topic of Unit 5, which is about the thermal energy. In this topic, we'll discuss how a thermal energy transfer as well as uh, specific heat capacity and specific latent heat. So how we define a heat energy? Heat energy refers to sum of kinetic and potential energy of the molecule or particle, also known as the internal energy. And to explain the idea of the internal energy, we use a concept of a temperature. What is temperature? Temperature is basically average kinetic energy of the molecule. It means that temperature explains the motion of a molecule. If high temperature means greater kinetic energy or high speed, the particles are moving. Low temperature means the particle will move slower. The lowest possible temperature, which is known as absolute zero, which is about minus 273 degrees centigrade. And at this temperature, what happened? The particle have the minimum possible kinetic energy, and the particle energy is directly proportional to absolute temperature. So that's why we can say that if we increase the temperature, the kinetic energy increases. So if we decrease the temperature, the kinetic energy will decrease, and at certain temperature the kinetic energy is minimum or zero, and that is the 0 Kelvin, or also known as minus 273 degree centigrade. So according to kinetic theory, when energy is supplied to the object, the particle increases the kinetic energy, they will move faster. In solid, the particle vibrate. In gases, the particle can move around each other at high speed. And if the average kinetic energy of the molecule increases, the temperature will also increase. So we can relate the temperature with the kinetic energy of the molecule and as well as speed at which the molecules are moving. Then specific heat capacity. Specific heat capacity refers to how much energy is needed to change the temperature of a 1 kilogram object by 1 degree centigrade or 1 Kelvin. So example, we have an object, say, which is 5 kilogram, and we supplied heat energy, we supplied 1000 joules, and its temperature changes from 20 degrees to 22. So specific heat capacity means how much energy is needed to change the temperature of 1 kilogram object by 1 degree centigrade. So 1000 joule is used for 5 kilogram, but we need for 1 kilogram. So it should be 1000 divided by 5. And for every 1 degree change in temperature, because in the question, when we are supplying 1000 joule, that is causing a 2 degree change in temperature, but we want only 1 degree. So that is why it is divided by 2. So the total energy supplied divided by mass and the temperature change. So here 1000 divided by 10, which is equals to 100 joules per kilogram degree centigrade, or it can be Kelvin as well. So amount of energy required to change the temperature of 1 kilogram of a substance by 1 degree centigrade, we call that as specific heat capacity. So specific heat capacity formula, specific heat capacity is how much energy we supply divided by mass and temperature change. We can represent by delta T, or we can use delta theta. Both are acceptable. Even you can write delta T, where E is the energy which we supply, M is the mass, and delta T is the temperature change. So this formula shows that specific heat capacity is proportional to energy supplied. Like if we supply more energy, normally specific heat for every material is constant, but if the material required greater amount of energy to change the temperature by 1 degree, it means it is having a higher specific heat capacity. And it is inversely proportional to mass. If we have a lighter object or small object, that will have a higher specific heat capacity and it is inversely proportional to temperature change. So if the object shows a small change in temperature, it means that will have the highest specific heat capacity. So it is a comparison, like if you have two objects of different mass and we supply the same amount of energy, like 100 joules for object A and 100 joules for object B. This is 2 kilogram, this one is 1 kilogram. And this cause example the temperature to change from 20 to 21, and this also causes the temperature to change from 20 to 21. So when we supply 100 joule, that causes a change in temperature by 1 degree for 2 kilogram. So the specific heat capacity will be 100 divided by 2 into 1, so that will be equal to 50. But when we calculate for the second object, that is 100 divided by 1 into 1, so that is 100 joule per kilogram degree centigrade. So it means if the two objects have the same change in temperature and absorb the same amount of energy, the one which is lighter will have a higher specific heat capacity. So specific heat capacity is amount of energy required to raise the temperature of 1 kilogram by 1 degree centigrade, or can be by 1 Kelvin. So example, an aluminum saucepan is there which is 400 gram containing 750 gram of water that is heated on a gas hob. How much energy is supplied to bring the water from the room temperature, which is 18 degrees centigrade, to its boiling point, means 100. The specific heat capacity of a water and aluminium is, for water it is 4200 joule per kilogram Kelvin, and for aluminium it is 910 joule per kilogram Kelvin. So basically what happened when we supply the heat energy, so because the water is there inside the aluminum pan, so the aluminum pan temperature will increase as well as the water temperature will also increase. So the total energy which is absorbed, what we can do, we can work out the total energy absorbed by the aluminum. So we have E is equals to Cm delta T. And again for water, this will also be E is equals to Cm delta T. And then what we do, we will add the energy absorbed by the water and energy absorbed by the aluminum to change the temperature from 18 degrees centigrade to 100. And keep in mind, when temperature change is there, the temperature change in Kelvin is equals to temperature change in degree centigrade. The temperature change are same. And whenever specific heat is joule per kilogram Kelvin, the mass should be in kilogram. So here mass is given in gram. We have to convert into kilogram. But when I say temperature change in Kelvin is, I'm not saying temperature in Kelvin equal to temperature in degree centigrade. But the temperature change in the Kelvin is equals to temperature change in degree centigrade. Like as you can see, this is 18 degree and the boiling temperature is 100. So 18 degree, when we convert into Kelvin, 18 plus 273, that will be 291. And so this is 291. And 100 plus 273, that is equals to 373. So when we calculate the temperature change, it will be 373 minus 291. So that will come out as 82. So the temperature change is 82 Kelvin. And same thing in degree centigrade, when we calculate, this is 18 and 100 minus 18. So that will also be 82 degree centigrade. So when the temperature is changing, the change in temperature in degree centigrade is equals to change in temperature in Kelvin. So if we are in the formula, we have to substitute the change in temperature. Then even if you convert the unit, that does not make difference to the answer. So first we'll find how much energy is absorbed by the water and then by aluminium, or it can be other way around. So to know the energy absorbed by the aluminium, the mass of aluminium, that is 400, which is 0.4, multiplied by 910, the specific heat, and multiplied by temperature change, that is 82. We multiply, we'll get the energy in joules. And same way for the second, this will be 0.75 multiplied by 4200. Why 0.75? Because the mass is given in gram. And the temperature change, again 100 minus 18, or it can be 373 minus 291. So we'll get again 82. So we'll get the energy absorbed by the aluminium and energy absorbed by water, and the total energy will be the sum of the two, so which will come out about 290 kilojoule. Is it clear how we work out the energy absorbed by water and aluminium as the temperature changes from 18 degrees centigrade to 100 degree centigrade? Then you should be able to plan an experiment to work out the specific heat capacity. So as you can see, the formula for specific heat capacity is energy divided by mass into temperature change. But practically what happened, energy we cannot find directly because we don't use normally Bunsen burner. We normally use electrical heater. So electrical heater energy is power multiplied by time, and power is voltage into current. So we can say energy is VIT. So energy is VIT divided by mass into temperature change. So specific heat capacity is VIT divided by mass into temperature change. So C is equals to VIT divided by M into delta T. So V is a voltage, we will measure by a voltmeter. I is a current, we'll measure by ammeter. T is the time for which this heater is switched on. For how long we use this heater, so that's T. M is the mass of this block, if you are finding for block. And what is delta T? Delta T is the change in temperature, that is the difference, which is final minus initial. So at first what we will do, at first we'll make two holes in a block because we want to find specific heat capacity of a solid. So we should be able to place the heater and the thermometer in the solid. That's why we are making two holes. Then measure the mass of the block. So we'll have the mass here. Then measure the initial temperature, because temperature change can be calculated, but measurement is done. First we measure the initial temperature, then we switch on the current and the stopwatch at the same time and wait for a considerable rise in temperature, and measure the current by using an ammeter and voltage by using a voltmeter. Then switch off the current and the stopwatch and record the final temperature and time from the stopwatch. So we have all the parameters, and we consider that the energy gained by the block is equals to energy gained. So energy supplied, basically here energy gained by the block is equals to energy supplied by the heater. So C, and the formula specific heat is VIT divided by M delta T. So we'll use this formula and we'll get the energy. What are the precautions, safety precautions? You should use a gloves to handle the hot object. Use a lagging around. So we should use a lagging or insulation which will reduce the heat loss to the surrounding. Add oil in the hole to ensure proper conduction. Like in these holes we should put oil so that it can conduct, like there's a transfer of heat energy. And wait for some time after switch off the to a final temperature so that it reaches the thermal equilibrium. Oil, yeah, it in this case, because basically there should be a medium. If there was air, they're already in contact with each other, like a thermometer bulb is in contact with the metal. But just to improve the conduction, we put inside a liquid, so what will happen? Two processes can happen. One is the conduction by in contact between the two surfaces, and the other one is by convection within the liquid. So it's just an improvement that relative conduction or relative transfer of heat energy will be greater. Then specific heat capacity of a liquid, the same procedure is there, but liquid, because the heat is not easily transferred, so we should stir them continuously. And normally for a stirring, we can use this thermometer or we can use a normal stirrer. The same procedure is there, same method. So we have the formula C is equals to VIT. V is the voltage, I is the current, T is the time for which heater is switched on, M is the mass of the liquid inside, and delta theta is a change in temperature which can be measured by final minus initial. But because the liquid does not conduct quickly, so we should stir that so that uniform mixing will be there and it will have a uniform temperature throughout. Then what is the concept of internal energy when material, as we know, material is made up of particles and these particles are continuously in a state of motion. These particles are not stationary, they are continuously moving. So as these particles are continuously moving, they will have two energies. One is a kinetic, another one is potential. So when we sum up the kinetic and potential energy of all the molecules, what we call that as internal energy. So internal energy is the sum of kinetic and potential energy of all the particles which are present within the system. And in ideal gas, the potential energy is zero. What is the ideal gas? The ideal gas having, like example, the force of attraction between the molecule is no force is there between the molecule. In practical, there is a force, but in ideal gas, we assume there is no force between the particles. And number two, their collisions of the particle are perfectly elastic. Elastic collision means the kinetic energy is conserved, speed at which the particle moves towards the wall and it bounces back, that does not change. So in ideal gas, the potential energy is zero since there is no force of attraction between the particle. Therefore, internal energy is due to kinetic energy of the molecule. So ideal gas, following this postulates that it is like force of attraction between the molecule is negligible, as well as the collisions between the particle as well as with the wall are perfect elastic. But in reality, the collisions are not elastic. So the Maxwell-Boltzmann distribution graph is there, which shows how the energy is distributed among the particle. So what happened, as everything is made up of particle and these particles have energy, but they don't have the same amount of all the particles in even within the same material does not have the same energy. Some particles will have low energy and some particles will have high energy, but most of the particles will have average energy. So like the energy is distributed among the particle, but some have high, some have low, but most of them have average energy. So the individual velocity of each molecule in a gas is random. So when like they are it's not like there's no order, so it is random in this range from very slow to very fast. And the kinetic energy depends on the speed at which the particles are moving. So if we plot a graph here for energy of the particle and number of the particle, as you can see the graph between the fraction of the particle and the kinetic energy. So you will find at low temperature, greater number of the particles will have lower energy. So greater fraction of the particle have lower energy. But when we increase the temperature, the peak will decrease and the peak of the graph is shifted towards the right hand side. It means now greater number of the particle will have energy or higher energy. And this is also a Maxwell-Boltzmann distribution graph used to explain how the reaction is affected, or rate or speed of reaction is affected by temperature. So when the, like, this is a minimum possible energy at which the reaction start. So particle or area after that is known as the particle which will form a product. So when we increase the temperature, peak will shift toward the right hand side and the size of the peak will decrease. So greater area of the particle or greater number of the particle will have energy more than activation energy. So this shows that the rate of the reaction will increase. What are the characteristic shape of the graph? There are no molecule with zero energy. Like as you can see, when energy is zero, the number of molecules are zero. Then only few molecules have high energy. Few of the molecules have high energy. And there is no maximum value. So basically, these graphs, whenever we are sketching the graph, we should not touch the x-axis. Why we should not touch the x-axis? Because we cannot say that this is the maximum energy particle can have. The particles can have any energy. So there is a maximum value. So when we complete the graph, the correct way to draw this graph, don't touch the x-axis. If you touch the x-axis, it means you limit the maximum energy. Like this is the maximum energy which particle can have. But there is no maximum energy. That's why we should not touch the x-axis. And if we increase the temperature, the height of this peak will decrease and it will shift or more towards the right hand side. And the distribution of energy depends on the temperature of the gas. If we increase the temperature, the average kinetic energy will increase. So maximum particles will have higher kinetic energy and distribution will become more spread out. So according to this Maxwell-Boltzmann distribution, there are particles with low energy, there are particles with high energy, but most of them have average energy. Then what is the concept of a root mean square speed? Basically, when we try to calculate the average speed is a scalar, but if I want to calculate the average velocity, so if I want to calculate the average velocity of the particle, like example, if I, as we know these particles, we assume they have perfectly elastic collision as they bounce back. So if I say this is 300 and this is also 300, but average velocity, if this is positive, this will be negative. So to take an average, like example, if I say particle 1 energy is V1 and particle 2 energy is V2. So when I try to take an average, one is moving towards the right, another one is towards the left. So it will be 300 plus and then minus 300 and then divided by 2. So 300 plus minus 300 divided by 2. So average will be 0. So when we try to take an average velocity, we cannot get the correct answer, because if we are getting average velocity 0, it means it should be 0 Kelvin. But it is not 0 Kelvin. The particles are moving. So to overcome this constraint, what we normally calculate root mean square speed. So what we do here, because velocity, this is positive. If one is positive, the other one is negative. So how we can make both of them positive? So first we square them. So if we square them, both will become positive, because square of a negative number or square of a positive number are positive. So we'll square them, then we will take an average and add the last, because we square. So what is the opposite of square? The opposite of square is root. So they will take a root. That's why we call that as VRMS, root mean square. But actually, how it is calculated? First it is a square, then is a mean, and then it is a root. In terms of name, it is root mean square, but in terms of calculation, first we will square the velocity, then we will take a mean, and then we will take a root. So example, there are 5 different molecules are there which are having different speeds or velocities. So first what we did, we square them, like 500 square, 520 square, 501 square, 545 square, and 505 square. First we square. Then we take an average. How to take an average? So add them and divide by the total number. So it's 5. And then at the last, we'll take a root here. So when we take a root, this speed which we'll get, we call that as root mean square speed. Mean square. Then the molecular kinetic energy or kinetic energy of the molecule. The average kinetic energy of the molecule in a gas is proportional to absolute temperature, and the relation is kinetic energy. As we know, kinetic energy is proportional to temperature. Kinetic energy is given by half mv square, and whenever we substitute v here, so that v is a root mean square speed. Root mean square speed square. So that is the average. This is a sign which we use for average. So it is, and this is the average speed square, or root mean square speed square is there. So it is proportional to temperature. Whenever we replace the proportionality sign, we replace with equal to and constant. So what are the constant here? When we solve this, we will find it is 3 by 2 kT, where k is a Boltzmann constant, which is having a fixed value 3 by 2, also constant. So we can simply say that half mv square is equals to 3 by 2 kT. So this formula we can use to work out the temperature if we know the speed, or we can work out the speed of a molecule if we know the temperature. And this formula shows that kinetic energy, which is half mv square, is equals to 3 by 2 kT. So if we have two containers at same temperature, for example, this is 30 Kelvin or 300 Kelvin, this is also 300 Kelvin. So we have two gases inside the container A and B. In container A, we have oxygen, O2. And container B, we have nitrogen. So mass of oxygen, 16 times 2, so 32. Mass of nitrogen, it is 14 multiplied by 2, so 28. So when we have, like, when we compare the mass, oxygen molecule are having more mass as compared to nitrogen molecule. But they have the same temperature, so it means they have the same kinetic energy, or they have the same half mv square. So half mv square, how both have the same half mv square? So as we know, the nitrogen is having a more mass. So if nitrogen is having a greater mass, its particle will move slower. Sorry, oxygen is having more mass, so its particle will move slower. When nitrogen is having less mass, its particle will move faster. So when we work out the root mean square speed, here the molecules will move faster, here the molecule will move slower. But the half mv square for oxygen should be same as half mv square for nitrogen, because they are at the same temperature. So if you have even a mixture of a gases at same temperature, the one which is lighter will move faster and the one which is heavy will move slower. So this is a heating curve. Whenever we supply the heat energy, so first initially what happened, the particle will move faster, so solid temperature increases. Whenever there is a change in state, there is no change in temperature, because the energy is used to break the bond. So here the solid is converting into liquid. Once all of the solid converting into liquid, then the liquid temperature increases, and again at certain point where the liquids start to boil, a liquid start to turn into gas, the temperature won't change, and then at the last we will have gas. So temperature at which the solid is converting into liquid we call melting, and liquid is turning into gas, we call that as boiling. And the energy supplied in this part, that is known as the latent heat. Latent means hidden heat, because the effect of the heat is not visible here. That heat causes the temperature to change, but in this case the temperature is not changing. Why? Because the energy is used to break the bonds. So if you want to calculate the latent heat of fusion or latent heat of vaporization, so we can use this formula, that latent heat is equals to energy divided by mass, where E is the energy needed to change the state and m is the mass of an object, because specific latent heat is energy needed to change the state of 1 kilogram substance by 1 kilogram substance without changing temperature. Then using a kinetic theory explains the behavior of the particles. So using a kinetic theory, we should be able to explain the Boyle's law. So according to Boyle's law, the pressure and volume are inversely proportional. Or we can say the product of pressure and volume, whenever two quantities are inversely proportional, their product will be same. So the graph for inverse proportional quantity, it will always be an inverse, like a curve. And whenever we take any 2 points, like this volume is V1, pressure at this point is P1. This volume is V2, the pressure at this point is P2. So when we take a product of pressure and volume at point A, and we take a product of pressure and volume at point B, that will be same. But the condition, the number of the molecule as well as the temperature should be constant. So P1 V1 equals P2 V2. So this was about the beginning of a thermal energy. Any question or a doubt related to the session? So in the next session, we will do the question related to thermal physics.